Okay, I put the recorder in a different position. I'm going to try to get myself looking at the camera some. I'll look at you guys, but instead of the whole thing being inside of my face or the back of my head, that's if, you know, you guys can just shout out and say, remember the camera, Mrs. White, and I'll turn around like, oh yeah, I gotta look at you, and then that'll get me looking at you guys too. So we kind of did a review last week of what we talked about last week. We talked about John Dalton a lot, but I gave you kind of that handout. Anything you pick up from that is good. The biggest thing I tried to emphasize was that your observations are important, that you have a perspective on the world that nobody else has. Even your brothers and sisters growing up with the same parents, you have a very unique view of the world. And so when you make notes in your book, you may notice something that no one else has yet. Or make, oh, what if we did this? Or I wonder about that. You never know where that might lead. I could give examples of where it really did make a difference. That somebody wrote something down in their journal and then they went back and went, wait a minute, and made a connection that was really cool. How are you doing, Ben? Good. You sit way in the back and I hardly ever interact with you, but I'm going to try. I'm going to try to do some more interaction. So to keep it simple, because we've got a bunch of things I want to cover, but I want to do it so that you guys get it, okay? I'm going to go back and talk about the atom. That was the quark. That was the quirky part, the subatomic stuff. That doesn't really apply to anything that you see around you, okay? That's not what's interacting when I talk about an atom, okay? There are certain things that interact with atoms. What do you think interacts when you have an atom? When you put two atoms together, what parts of them connect or disconnect or interact? Any ideas? What's in the center of the atom?
A core.
What?
A core.
Yeah, those are inside these pieces. So let's back out. We're going to back out just a little bit. Not talking quarks, but what's
A core.
A core? What's that core made of?
Nucleus.
Okay, this big thing is the nucleus, okay? Although it doesn't have a ring around it. Okay, these are just pieces that are sticking together. Keep going. You've almost got it. You started out right. Neutrons. Okay, so you may have some neutrons. What else might you have?
Protons.
A proton. Okay, let's just do it like this.
Yeah, when you have a neutron and a proton, they want to stick together.
Yes, this neutron will stick close, and we could go get into the quark, but we're not going to do that. Let's say it just has one proton. The one proton is what gives it its name. If you look at your periodic table, there's a box up in the top left corner. Every box looks the same. You have a letter, you have a number here, and you have a number here. And I think there they give you 1 point there, right? And then underneath it, they actually give you the name. Everybody see that? What's its name?
Hydrogen.
Hydrogen. This number in this top left corner, okay, is called its atomic number. That tells you how many protons are in the nucleus. So the hydrogen has 1 proton, okay? So now, right now, he's got a charge, doesn't he? Because a proton has a positive 1 charge, he's actually electrically charged, okay? Atoms are not charged, they're neutral, which means I have to have something cycling around them to negate it. And this is a tiny little particle out there called the electron. Okay? And it has a negative 1 charge. So if you have a positive 1 and a negative 1, they cancel each other out. So the overall atom doesn't have any charge at all. Okay? What happens if I have 2 protons? How many electrons are in there? You have to have 2. What if I have 50 protons? You'd have to have 50 electrons. So the good thing about that number is it tells you the number of protons and the number of electrons. Okay. What it does not tell you is the number of neutrons. That has to be calculated a different way, and I'm not going to worry with it right now. I'll teach you that eventually. Okay. like in another class in chemistry, you'll deal with that. Okay. Hang on. We're going to get to that. Okay. But I'm just trying to get, so when I say atoms, we're talking the number of protons and the number of electrons. For now, you can ignore neutrons. Okay. Hydrogen's pretty easy. Okay. But let me show you, let's say, okay, I'll pick my favorite, my absolute favorite element. These are all called elements because they're as far down as they can go. Okay, a molecule is when you take a number of these and stick them together, but when it's all the same type, these are elements. And my favorite is fluorine, believe it or not. And I have no idea why. I mean, I said that in my biology class, and one kid just about fell over. He was, that is like the most reactive of all the elements. Whoa, this is in my biology class. Yes, the most reactive of all the elements. That's kind of a broad statement. I guess I'm trying to think of anything else that would be wrong. No, he is the most reactive. He will react with everything. Fluorine, F. And he is number 9. Now, what does the 9 tell you? He has
9 electrons and 9 protons.
9 protons, 9 electrons. Okay. This number over here, 18.9, that's how much mass it has. It's not really weight. Okay, it's mass. And I'll tell you the difference in mass and weight just for fun. Okay. What you weigh here on Earth, let's say, okay, I weigh 130 on Earth. Do I weigh the same on the moon? No. Why?
Because of the gravity.
Because of the pull of gravity, right? But I have the same amount of, it's like I don't shrink because I go to the moon, right? I'm the same pieces. So my mass didn't change, but even though my weight changed. So there's slightly different things. I'll tell you something else really cool, okay? Because there's nothing atomic, the atmospheric pressure. Okay, but once we start putting more protons into the center, something interesting happens, okay? Let's say now there's 9 protons. 1, 2, 3, 4, 5, 6, 7, 8, 9. Obviously, it's not going to look like this because there's going to be neutrons all stuck in between them. How many of you have taken 2 magnets, okay, and you take their like charges and you try to push them together? They won't stay together. Yes?
Oh, you said how many of us?
Yeah, okay. Yeah. And you can't get them to stick together. Now here I've got 9 positive charges. They're not wanting to stick together. They're trying to push each other apart, right? That's what the neutron does. The neutron gets between them and says, it's okay, guys. It's okay. It's okay. It's okay. You don't have to go away. And that neutron kind of helps hold all those positive charges and keeps them from fighting, if you can do it that way. Okay? So that's what the neutron does. He keeps that center where it wants to stay together. Well, because we have, and then we have now 9 electrons. Okay. Humor me. I'm just drawing things very simply. This is all I expect. Okay. The electrons cycle around the nucleus at a distance, which is also quite amazing. Because what if I had a -1 charge and I've got all these 9 plus charges in here? What's it wanting to do? Right? Now I've got a positively charged center and a negative, tiny little element, tiny little particle out here. It would want to get sucked into it, right? The only thing keeping it away is energy. It's got a certain amount of energy that keeps it at a distance. Okay, this is the first level, and it can hold 2 electrons. Okay? Then there's another level out here. We're going to call these energy levels. Okay, if you can think of it that way. It takes a certain amount of energy to stay there. It takes a little more energy to stay out here. Okay, it's wanting to get pulled to the center, so it takes more to be out here. And it will hold 2 also. That's 2, 4, 6, 8. It's not quite like this, and I'll maybe tell you why, but maybe. Right now, I just want you to think of it like that, okay? I want you to understand they're not all circles. Inside these energy levels, once you get to the 2S level, one is a sphere, one is a dumbbell. It can rotate in like a big figure 8, okay? And it'll hold 6 of those. So you've got 6 of them still on the same energy level, but in a different shape. I don't want you to worry about shape. We'll worry about shape in chemistry. What I want you to think of are energy levels, okay? Obviously, once I fill all this up, there's another level outside of there, isn't there? I mean, you can just imagine. Imagine them all drawn in, right? I'm not going to draw them all in. But out here, we've got these electrons, and even outside of that, there's another energy level. Okay? For him to get from here to here, has to have a certain amount of energy inside of him to be able to jump out to that next level. Doesn't want to be out there. It's more comfortable at home. Kind of like me. I really like being at home. If I go to town, it doesn't take me long before I really want to get back home. So he can be forced out here, but he doesn't want to stay. And I call them he's. Sorry, girls. It's just a default method. You know, I don't mean it. And it could be a female out there trying, but she likes to be home too. So it all applies the same way. So here is where this whole spooky idea of quantum. If you hear somebody say, I'm going to talk about quantum mechanics, you know, you go, don't have to. All quantum means, okay, quantum, just think of it as a little packet. Okay, a little bitty, you know, at weddings when they make those little bitty pouches with like the rice in them, think of it kind of like that. Okay, it's like this little bundle of energy. That's all quantum means, is that energy comes in little bundles. It's not like single things all threaded out. They're little bunches of stuff. Okay? So in other words, we take this fluorine, for some reason we decide to light it on fire. Okay? Which we wouldn't do, I promise you, but because I like fluorine too much. But if we light it on fire, okay, that's energy. Heat energy goes into this atom, and these electrons are forced to jump out to the next level, energy level out. Okay? It doesn't want to be there. It wants to go home. So it has to get rid of energy. And you know what he does? He emits 1 photon of light. Poof, and now he can drop back home. But probably the heat is still there, which forces him back out. And poof, another little photon of light, and he drops back. Okay? So that is what light is. These little photons of light are that electron jumping to an outer level, releasing energy, and dropping back in. Okay? That's where light. That's where light comes from. Electrons leaping within elements. Yes.
Is that why you touch electron hot?
No, that works a little. We'll get more into that on electricity, because that light. Well, it is, but it isn't. That little tiny, you know, inside your light bulb. Oh, that's a terrible light bulb.
Hey, I'll draw you one.
No, it's okay. There's these 2 little things, and then there's a tiny little cord, tiny little metal piece that connects the 2.
Yeah.
Have you ever tried to look and see, is this light bulb any good? And you look out and there's this little thing is broken and it's hanging there. Okay. It's the energy going across that fine filament, and the electrons inside that filament are jumping back and forth. But it also makes it get really hot. So the heat is more
Of the electron.
yeah, the electrons moving through, and it's more than, yeah. But that is where the light comes from still though.
Actually, no, I'm trying to get out of this little tiny environment.
Yes, exactly. That makes sense. Yes.
Like when your bulb goes to turn on and it goes like on and off, does that have anything to do with the electrons?
Again, yes and no. Okay. Mostly it has to do with this little fine filament. You're going to make a filament for a light bulb next unit. You'll work more with electricity. I mean, you're going to generate. Anyways, this little thin wire may be getting a point in it where it's just about to burn through, and yet it's still touching every now and then, so it's coming on and off. So it's more about the filament than. But deep down, that filament, it's the electrons. Any other questions? That's good. What do you think of this? Is that pretty cool? Did you understand? Yes.
So how do LED light bulbs work? Like, do they have the same like rigging that does, or because I know like my dad's an electrician, so I hear like LED is better than regular all the time, but I don't know how LED works.
Yes. I don't know. I can look LED up and tell you that more next week. But I bet it has to do more with lighting a gas instead of it being a filament that's being heated. It's a gas possibly. Because I don't even know what LED stands for. What does that stand for? Lighting. We'll have to find that out. Do you know? Okay, yeah, okay. So, like last week, you had to skip all those atomic exercises. This week, when I say, look at your periodic table, and you can just pick any one of these elements and say, okay, that's right.
138.
Oh, did that pass? Not in that book. It's got to be right in here somewhere. Kind of flip through. Okay, because that's just the first part that I wanted. There it is.
Page 138.
Yeah, well, it was 138. I guess I read the wrong number. Sorry. So all you're going to tell me is you're going to pick an element. You're going to tell me how many protons, how many neutrons, and then you might say, well, what about this energy level thing? Yes.
How do I figure out the neutrons? You said
Oh, I meant electrons, okay. Not neutrons. You don't have to calculate neutrons. If you want to tell me the mass, like that 18.9 or the 1.0, that's fine, but that doesn't really mean anything to us right now. Okay, not until you get into chemistry and start working more with weights, and then that atomic mass is going to come out to be really important. So right now, just protons, electrons, and energy level. You're like, how do I know how far? Do I have to draw this every time? No, actually, the periodic table is so cool, guys. This arrangement, you can look at it and tell exactly what the structure is. Once we get more into shapes and stuff like that, if you stick with me on that. But if you look at the shape of this, you'll notice that they're in rows, right? These all occur in rows, okay? This row has a 1 out beside it. That's first energy level. Second energy level. Oh, look, third energy level. But this is not telling you all of the electrons. This just tells you the ones that are the farthest out. So for instance, when we get down to, is it radon? When we get down to radon, let me find them. Radium, number 88. And he's in the 7th energy level. You see that? 7th energy level. That just means the outermost electron, the very last electron that's out there is in 7. Okay. Because when we work with these, really the only important ones, these center ones never do anything. I mean, as far as they don't interact with anything. The protons don't interact with anything. Okay. If you have 2 big basketballs and you bump them together, well, the centers don't interact at all. It's these outer edges, right? So your outer 8 electrons are really the only ones that do anything, okay? And they're so important they have a name. Okay? I'll tell you that. Valence electrons. I don't want to require it. I don't want to get too deep. Yeah?
But when you said plastic balls, they're full of air, but they don't float. It's hot air balloons. They float.
It's true. That's very true. But if you bump them together, the only thing touching is the outer surface, not anything in that center. Okay? So those outermost electrons are the most important ones. Maybe I'm going to wait. We'll talk about valence electrons next time. Next unit in electricity. Okay? So, but then we want to say, all right, so that's where a photon of light comes from, but what is it? What is light? Okay?
It's, I don't know,
Tell me,
it's,
what's the definition?
an atom gets two, it's either protons or, I think the electrons, two the electrons, so it pushes the electron off, and it shoots into the next one. And that one doesn't either. So it shoots
That's
next one.
electricity. That's electricity. I'm thinking of light. Okay, does anyone have a definition of what light is? Have you ever heard of it? Everybody's telling me fire. You heard of anything?
Fire,
What?
fire.
Fire makes light, yeah. Okay, let's give it a definition. It is an electromagnetic wave. Okay? Electromagnetic wave. You're like, oh, okay. Well, this is really not that hard. This is a combination of electricity and magnetism. Okay? But before we talk about that, you have to understand what a field is. Okay? An electric field or a magnetic field. You ever heard of those?
Yeah, I have. I've heard of.
Okay, so like if I have a magnet, okay, I have a funny looking bar magnet. Just don't laugh at my magnet, okay? Then it generates this attraction all around it, okay? As it's close to, let's say this is the North Pole and South Pole of the magnet, okay? The magnetic radiation or magnetic attraction looks more like that, okay? Things are really pulled here and they're really pulled here. But as you move towards the center, they kind of get this long, laid out kind of look to them, okay? Okay, and if you don't believe me, I'll show you. So, this little thing is full of iron filings. Hey, you can really see it on the camera. That's really cool. And here is my magnet, and I'm going to put it inside here. I'm going to twist it. Okay. And you should be able to see that it creates a field. Let me hold it up right here so you can see it.
Oh,
You can see how it stands out at the end, and then in the center, it kind of lays out flat, okay? Meaning that if you were dead center, it would be equally pulled that way as that way. So it just kind of is in a stagnant mode. But as soon as you start to move this way, it gets pulled farther. You can pass that and you can kind of look at it. And then you can move it back and forth and you can see it change. Kind of pass that along as you continue to listen. Okay, everybody will get a good look at it. And the magnet will fall out at the end. So that's what the field looks like in a magnetic setting. The same thing occurs in an electric setting. Okay, same type of a structure. So you're like, okay, electromagnetic field. There's so many cool things to tell you about it, but I'm going to be really careful because I want you to be amazed and not bogged down. There's plenty of math we could do with it, but I'm not going to do it. So what happens is it's widely known. It has been widely known for many hundreds and hundreds of years that if you change this field, like if I take that magnet and I wave it around, okay, well now you can tell everywhere I move it, it's changing that field, right? It's actually generating a little bit of electricity, okay? And if you change an electric field, it will generate a magnet. For instance, if you take a battery and you hook it up to a nail, the nail becomes magnetic. Even though electricity is flowing through, it generates a magnet. Right? Everybody familiar with that? Those great big, what do they call it? Those great big machines that you pick up cars with magnetically. What are those things called?
Magnetic cranes.
A magnetic crane. That's what he's doing. He's running electricity through this metal piece, and it's creating a magnet. Yes.
So if you put a battery in a nail, it makes a nail magnet, so the metal pieces will stick to the nail.
Mm-hmm. But you have to be careful because you can also shock yourself doing it. I did that too.
It hurts.
It did hurt.
Well, that's not as crazy as what my brother did. He put it on his tongue.
Oh no, that's really funny. Yes.
I think that I'm thinking of but there's a thing, and you'll hear the term a lot in movies, a hydrolift, especially
Yes.
like in futuristic movies. I don't know if they've made a real life version yet, but I know that for a while they were testing out making a hydrolift using magnets and
Interesting.
magnetism.
Exactly. I bet it would work too.
I
That'll
don't
be-
know how effective the stop would be, but
Yeah, that's true. It's the stopping that's the issue. Okay, so when this electron drops down and emits, and we're calling it a photon of light, you're like, well, what's it doing? It's sending out some energy. Every time you change a magnetic field, so I take, let's say this is my magnet, okay? I'm changing that field, right? Because I'm making this that's all sticking this way, and I'm moving it around, okay? I'm moving that field. It's following the magnet, but I'm moving it through space, right? So every time it changes, it generates an electric field that starts. Now, because I'm not doing it consistently, we don't have anything to pick it up, we can't see it. But it kind of looks like, well, I need to give you one more definition. The last thing, the wave, okay? Light also acts like a particle, but for today, we're just going to talk about the wave, okay? So I'll probably, on your exercises, tell you to take your compass this week. I want you to practice making circles with that compass. Your mom will get you one. Okay, in the compass that I wanted you to buy, there's a little wheel that you can turn in the center, and it makes the fork, bigger or smaller. I want you to set it, learn to put it on your paper, and draw a nice circle that doesn't get wobbly. The hard part is holding that center point down so it doesn't move around, and you get a nice clean circle like that. Okay. So you can use that to make a wave. Okay. Just because you'll probably use some extra practice working with that compass. Here is your baseline. Okay. And my wave is going to look something like this. It's going to go up and it's going to go down. It's going to go up. It's going to go down. Hopefully I didn't stay the same. It's supposed to stay the same. You just have to use your imagination with my drawings, okay? This is a wave. It's got a top part called the crest, okay, which is what we call it at the ocean too, right? The waves are cresting. That's the top, then it's flipping over the top, okay? The crest, and this is called the trough. The crest and the trough. This is the baseline. You won't worry about it.
If the waves, the top is supposed to do the same.
Yeah, you should. They should. And that's why if you do it with your compass, and you're going to set your compass and you're going to spin it around and then stop, and set your compass again and spin it around the bottom, then you're going to have very nice, even, smooth waves, okay? So that's all fine and dandy, but the really important one is the distance from here to here. The crest of one to the crest of the next one is called the wave length. Okay? The wave length. That's how far apart the waves are. At the ocean, if it's a nice, calm day, And maybe the waves still come in, right? It's never just totally still. There's always still some waves coming in. But those wavelengths are way far apart. So if you're standing where the water's hitting your legs, it might go splash, splash. Okay, that's like, it's a really long way, okay, before the next crest gets to you. If it's a windy day, right? What do you think is going to happen?
Big waves.
Big waves, just big waves, right? Or usually it's like, it's just all a big tumble by the time it gets to you. So think of it this, the longer the wavelength, okay, that's called frequency. How frequently does it hit your leg? Okay? If the wave is long, the frequency is low, right? If the wavelength is a higher number, this it's shorter, yeah. Okay, so like I'm gonna go another one, okay? Let's just say this one's going like this. Okay, you can see two of these crests, no, 1, 2, 3, 4, 5 of these are hitting in the same amount of time as one of these. Does that make, you following that? Okay.
6.
So, yeah, if the distance is shorter, the shorter the wavelength, the higher the frequency. Okay, so the short wavelength, do they understand that? Short wavelength, high frequency. That's the relationship between those two. Following that, Ben? Got it? Everything good? You feel like you're in another room over there? You like being in the back? Okay. I won't talk to you too much. I'll try not to. So I wanted to cover the parts, the wavelength, the crest, and the trough, that relationship. The wavelength makes a difference. Wavelength makes a difference when we talk about light, okay? The distance of the wavelength determines the color of the light, okay? So if you're seeing red or orange, okay, you're seeing an orange shirt, okay? Those wavelengths are pretty long. You're seeing a blue wavelength, okay? Blues are very, very short. Okay? Short wavelengths, yes.
How do you determine what color means long and short?
Because
Is it like bright and not so bright?
no, that has to do with amplitude. The distance from here to the top is called the amplitude, and that determines brightness or dimness. So I could have the same wavelength, but have it shorter, like if I'm terrible. So you can see, it's, well, I missed it a little bit there, okay? You see how it's still, there's my same crest, but now it's not nearly as tall. So this one would be dimmer, but it would be the same color as this one.
So it's like bright red and then would be shorter.
No, it would still be the same color. It would just, like if I had, it's like if you have those rheostat light switches that you can turn the thing and it goes,
Oh, yeah.
it doesn't change the color of it. It just changes how bright it is. So I'm going to tell you about the colors now. Okay, everybody got this? Is everybody hanging in there? You guys like ready to run away home yet? Please don't, because I haven't even shown you the elements yet. We haven't lit anything on fire yet. So for the spectrum, that's a good question. When you see the rainbow, it's always in the same order. Always in the same order.
It's not like you see the rainbow one day and it's red, yellow, black, and blue, and the next day it's orange, yellow, black, and blue.
Yeah, but you won't do that, right? It's going to always be the same, okay? Because the visible light that comes from our sun has a set number of colors. Now, when you get to maroon, you're going to get somewhere, you know, in a mixture between things. But it goes like this: red, orange, yellow, green, blue, indigo. Now that's a color most people don't know. Indigo is kind of a, yeah, I always think of it as being like that cerulean, like sky blue. This is like blue that's kind of more deep, and then this is like a kind of a brighter, and then there's violet. Okay? If you can remember this guy's name, Roy G. Biv, then you've got the right order. Okay? Red, orange, yellow, green, blue, indigo, violet. Okay? You'll want to know that so that if I were to ask you sometime which has the longer wavelength, so now I need to tell you this. Red is the longest. Okay? Violet is the shortest wavelength. So then all you have to do is start saying the guy's name. Now if I say, which is longer, green or orange, and you say red, orange, well, orange is longer. Whichever one you say the first, that's the longest one. Okay, and you say that name. Okay. Oh.
Oh yeah, I
Okay, she's got that one. You can keep it. Okay. You don't have a notebook. Okay. We talked about the frequency. Hey, we're doing great this time. What time is it? 12:30. Nice. You got like a half hour. I could do math this time. I am just teasing. Just teasing. So I wanted to kind of go through that wavelength and touch on that so that I can talk to you about the coolness of the fact that light generates its own energy as it goes. Okay, that changing of an electric wave creates a magnetic wave, and because that wave is changing, it generates the next hum. Okay, oh, my wave is gone. So here's kind of what it looks like because they work at 90 degrees off of each other. See if I can get this to stand up right. Okay, this one goes down like that. Kind of looks like that. You can imagine that one moving down. Okay. So they're at 90 degrees to each other. Imagine the red one, say, is my electric wave. The electric wave is changing, and as it's changing, it generates this magnetic wave. And as it's changing, it generates another electric. And as it changes, it generates. And that's what allows it to go through space. Okay? Isn't it great?
like a chain.
But it's a self-generating chain. It keeps going. A wave in the ocean has to actually push things, right? It's pushing water molecules up and down. So, yes?
Like the boats are so heavy they could sink it and stop. But the waves are trying to push it up because they don't like to be pushed down.
That's true. I can see that point. Yes?
I guess this is sort of like where if you could turn the sun on and off like a light switch, it would actually take 8 minutes for it to return.
Exactly. But only 8 minutes. That's a long span of space to cover.
So
in 8 minutes. It's moving.
light.
Yes, it's moving really fast. Are you going to say something? I don't see another hand. Okay. Well, this is what allows it to go through vacuum. Okay. You can have a vacuum tube and shine a light beam through it. We're used to that, right? We're just like, oh, yeah. It's just going right through. But it's not pushing particles. It's generating itself as it goes. So think of it as each time that electron moves away, it's this starting point, and it goes, and it starts this wave moving, okay? And then it sends out another one, and it's pulsing, and that makes it act kind of like a particle. We could talk about the particle theory. Right now, I'm just talking about wave theory for light, but light also acts like a particle. If it goes through a hole or something like that, it's acting more like a piece of something than a wave. The other, let me think, that's what I want to tell you about waves. I got that covered. Okay, so then the next cool thing, any questions? Am I giving you too much information? Anybody feel overloaded yet? A little overloaded?
Well, I mean, I couldn't sleep at all last night. Like, I've been awake for over 24 hours, so
So you're having a hard time hanging in there.
yeah.
Okay, I tell you what we'll do next then. Isn't that cool? Don't you like this feel? Okay, I just think that's good. I wish you could see it. There you can see the light.
You could borrow that from the book.
Yeah, you probably have. I learned it out. So let's take it back to elements. Okay, so you see these elements have their outermost electrons are in different levels, right? So that means that their electrons are out there at different energy levels. So if one is way out, and it's got a lot of energy, and it leaps out and leaps back, it's going to emit a light wave, right? Well, we just found out that the wave of that, the wavelength determines the color. So if I light different kinds of chemicals, I should see different types of colors, right? You want to do it? Yes.
I think so last week, but scientists made a new color or shade of blue.
Oh, yeah.
Yeah, so they like put different chemicals together to make that.
Yeah. I read that, but I can't remember.
It was like
Yeah.
they made
A different, yeah, it's
it
a
seems
different,
it doesn't seem different to our eye,
right. Deep down, it's a different structure.
but it's sort of hard to like think. People actually invented a new color.
Right.
It's really hard.
You just think, oh, it's just a variation of something that's there. Maybe it's just a different wavelength. You know,
Yeah.
now you can like, oh, okay, so they're talking it's a different type of a wavelength. So this is what's called a light spectrum. Okay, try to hold it up for her too. Maybe I can pass this too. These are different elements, and if you had one of these and you were looking at the light through this, okay, you would see these little distinct bars. Most of the time what happens, guys, is that it lights so fast that you can't really detect it with your eye. It's better if like you record it and then you can slow it down and go, oh, okay, there are those beams. So I'm not going to do this because then you do that and try to stare at it and it takes 2 seconds and it doesn't work so well. But this is how they can say, they look at the sun and go, oh, that's hydrogen burning. How do they know that? Well, they took pictures of the light spectrum coming in, and because it's emitting the same wavelength as hydrogen when it burns, they know hydrogen's burning there. Or they look at another star and they say, oh, it's got potassium in it because the potassium spectrum shows up in the camera. Okay, so they can determine what's on these stars by what the light spectrum. So I thought you'd want to see a couple of these. I'm not going to burn your book up. Yeah, I'm going to do it on that table actually. This one. And the other thing I may need, I'm hoping this thing lights. I'm hoping it lights. Actually, I need to put it on something.
Not wooden.
Yeah, something that maybe won't. Right. Oh, see now she's going to miss out on everything. I will do it here. I'm going to try to turn this on. Hey, now she can see everybody. Say hi. She's not even there. Whoever watches the recording will get to see this. And it's right against that light. And keep in mind that these wires are made out of copper. So when I burn it, there's going to be a tiny bit of copper that's burning in the loop itself. First, we got to see if we can get this thing to light. Can you give me a match, Erica? Yeah, please. So we'll have to light that. While we're waiting, I was going to tell you something else. Let's see.
What are those?
These are different chemicals that,
I see.
yeah, they make, what they do is they'll create a salt out of different elements. But what you'll see burning is not so much the salt part, but the actual elements. So this one is copper, and this one, I want to burn copper and calcium and strontium. You look at your periodic table, okay, calcium occurs in the 4th level, 2nd column. Calcium is number 20.
Yep.
Okay, copper is number 29. So you can see that he's got more electrons out there, right? And then strontium, okay, that'll work. Somebody find strontium for me. 52? Okay. All right, so let's see if we can get this in. So again, keep in mind that it's because, you know what, honey? Oh, I know. Can you hand me my little art case? I've got some water in here. No, I need to have something that I can, I'm going to like contaminate my little. Okay, I did this at home.
Strontium is 38.
Oh, really?
Well,
Which one did you say? What is 52?
That's 52. Tellurium.
oh, not there. No.
Oh yeah, the
Oh,
left
okay.
hand number, not the mass number. Okay, let's see if I can do this. I don't think I can write on it. Hey. We don't need it to be very right. And you see all that, the blue that you see is actually an element they add to the gas itself. Normally it would be clear, but they want people to know that it's burning, so they put this element in there so that when it burns blue, so that they, oh, there's the, just so you know, that is actually added to the gas. Yes.
What about whenever you burn it like a wood fire and you still see the blue?
Yep, that means that within that wood, then that element is in there. Usually that orangey color is carbon. Carbon has an orange flavor. I don't know. There's my leftover that I did yesterday. Okay. This is copper, because I think copper. Okay. So it burns green. And as long as there, of course, I said then my wire itself is also copper, so it's probably okay. I'm going to try to burn that off. Maybe I get too much. You guys think that's cool at all? It had a nice green look to it. Okay.
So is this how they like make the colored matches and stuff like that?
Yes, they put different elements on the ends of the match, and then when you strike it, it'll make the colors. Okay, so then that one I'm going to say. This one is calcium. So that one was copper. This is calcium. I'm going to try to not get quite so much. Not quite so much this time. Okay. Well, you're still seeing some of the green from the copper. It's more of the orange.
Blue.
Yeah, it's kind of got that blue in it, doesn't it? Let me put the blue. Calcium.
What is it supposed to be?
I thought it was supposed to burn orange. So
Well, yeah, there is orange.
there is orange there, but that is a very distinct blue there in the center. Maybe that's still that old copper. Okay, so really, I should have like 4 or 5 of these and not mix them. There's more orange. Let's try it one more time.
You should use the other one maybe.
Oh, no, that's a lot.
The orange.
Okay. Okay. Wow. Okay, we're like burning things up. How about that? That's pretty cool. Calcium carbonate.
Did it expand?
It did. Yeah, it just boiled it and then expanded it. Okay, and so then for the last one, I wanted you. So what color is copper?
Blue, green,
Green. It was more green, and then calcium was.
orange.
Okay, so this is strontium. Okay. See if I can get some. Yay! See, I'm still seeing some green though, so there's still some copper in there somewhere, and there's still
It might
some.
be your.
Yeah, it could be. All right, let's do a little more strontium, just a little more. Just so you can say you saw it. A little more. Okay. All right. So those are the different colors based on the wavelength of the light that's coming off. And those are the electrons leaping from these elements. Okay, so I'm trying to connect all of that for you. Plus, it makes something a little bit more fun than me just sitting there talking. Right? A little bit more fun. Let's turn this on. All right, we didn't catch their house on fire. That was a good thing. We didn't explode anything. I didn't burn any students. That was good.
Oh, dang it, I was looking forward
Yeah,
to
I thought so. I thought so, yeah. So that's, oh, you know what? I wonder if she was able to see. Imagine. Did anybody look at the camera?
No.
Could you
Nope.
see it? Yeah. Okay. Good. All right. So I'll put that away later. So let me go back and see what else I wanted to tell you. Because I know there was one more thing I wanted to cover. Oh, yes. So we've talked about this part. Okay. Let me make it a little smaller. Just one more thing and then we'll be done. Okay, and we're ahead of time. So this won't be too bad. Okay, and I'll let you out early.
I'm gonna text my grandma. And tell her
Okay.
I'll be listening.
Okay. All right. So this spectrum right here is what we can see. All right. Now there's a lot of light out there that we can't see. Just like there are sounds that you can't hear. Correct? You know, you have the dog whistles. Yes.
Isn't there a light of ultraviolet?
That's what I want to tell you about. That is true.
What the sun gives out that makes the sky blue.
Well, and the sun is emitting all of this light. Okay, all of this light. But some of it. So I'm going to put our little spectrum right here in the center. Roy G. Bid. Okay, there's the light we can see. Okay, and our wavelengths. Okay, each one of these has a different wavelength. In your assignment, it says list the colors in order, and out beside it lists the wavelength. Don't worry. If you can find the wavelength and you feel like writing it out, that's good. I mostly want you to know the correct order. Which one's the longest, which one's the shortest. Not so much the number of what its wavelength is. Okay? So you can kind of ignore that part. Okay? So, but there's, well, let's go her direction. Okay? She called it, so this last color was violet, right?
Mm-hmm.
The next size is ultraviolet. It means longer than violet. So it's the very next wavelength out. Okay? These are used for, let me see, what did I say in here? Okay, ultraviolets. These that go beyond violet. Violet is our shortest wavelength, high energy, high frequency. So these tend to be used for, well, the next one out is like the X-ray. What was ultraviolet used for? That will light up things that are fluorescent. it'll make them,
Glow in the dark.
yeah, glow in the dark things respond to this light. Okay, but it's not dangerous at this point. The next one out are X-rays. Everybody knows what X-rays are for, yes?
X-rays are for revealing hidden stuff.
Revealing hidden things, right? So when you break your arm or leg, they don't have to operate and look at it. You can look at it like right through your skin. So this will penetrate your skin. Yeah, I think we all have those have done that. So these are intense, and it can hurt you, right? The more energy that's hitting you, the more dangerous it can be. The last one out here are gamma rays, okay, coming from the sun. And those are, again, the higher that frequency, the more energy, the more intense, more damage it can do.
That's how the Hulk was made.
That's right. There you go. See, it can change you to the whole. So stay away from gamma rays. So the next one just below here is, if it's below, it's infra or infrared. Okay. It's no, they're long. The waves are getting longer. So think of it kind of like this, like here we've got really long, and then they're getting a little closer. Okay, think of it like that. The longer wavelengths are this way. Yes.
My dad had a helicopter that how he operates it is with infrared.
Infrared. Yes. These are yes.
Infrared is is like what they use in the technology to see in the dark and stuff, right?
Exactly. Shining through the dark, and also heaters. Okay, they heat things up. So most of those space heaters and things, they'll be using more of the ultra red. Okay, and then below ultra red is, I meant infra. Sorry, infrared. And infrared, and then I guess I'm just going to move all the way out here to radio. I'm trying to remember where microwaves are. I think microwaves are here. I think microwaves are somewhere in here.
Radio? Do you mean like
the radio station?
Yeah.
So we always think of it as, oh, okay, they're sending out a sound wave. They're not sending out a sound wave. Because if they did, it would hit the first hill, and nobody else would be able to hear that, right? Because sound doesn't travel, but they send it through light. They use a light wave and send sound pulses by pulsing the light, and then have a receiver on the other end that translates pulsing to sound. Okay.
Is that why lightning and thunder?
Exactly. Exactly. Because the light can move much faster than the sound wave can.
It can like go through the light.
Yeah. Exactly. So the radio waves are your longest waves, but if they're actually light. What?
It's like when it gets a lightning strike that messes with it or breaks it or whatever. Is that because it's already going through light? Like I know anything can be damaged by lightning.
Right. Yeah. Well, I think you mean what is doing the damage when the electric bolt comes through?
Yeah, I guess.
Yeah, that's more the electricity. That's it's an intensive. We'll do more with that in electricity. These two things are so closely related, but that's the big picture that I want you to see connected. Okay, the atoms, how they're structured, electrons leaping, sending out photons of light, and then understanding that it's a wave. The length of the wave determines the color. That's the other thing. Color. How do you see color? You know, how is his shirt emitting orange waves? Yes. Okay, your lens is taking everything in, okay? But if you look out at those clouds, what color is that? Gray or white, right? It's white. If you see the color white, it is every one of these wavelengths at the same time. So they kind of, they don't cancel each other out, or they enhance each other. So anytime you're seeing white, this white piece of paper, you're seeing every one of them at the same time. Yes.
I guess this is sort of like color is thinking of white and black. Black is the absence of a color, and white is also.
All colors put together. That's right. This white is every single color that's coming in from the sunlight. It's bouncing off this page. You're seeing all of them. The black, all these light waves are coming in and it's absorbed. It's sucking in and it's not reflecting any out.
Kind of like with you're not as hot when you wear white in the summer.
Yes.
As black when it's too hot.
Absolutely, because it's absorbing all the light waves and holding them in. Okay. So what's happening to his orange shirt is all the colors going in, everything's getting absorbed except for orange. Orange is being reflected back out. Okay?
That's how they make dye.
Yes.
Somehow. Maybe.
They combine the chemicals so they'll absorb different wavelengths and reflect other wavelengths. Okay? So when I say on your assignment, how do you see color? I'm not talking about just talking about your eyeball. I'm talking about color hitting things and reflecting off. If you see a barn and it's red, it's every light wave is hitting it. Everything's being absorbed except for the red. The red is being reflected off. Does that make sense? Clear enough? You hanging in there? Okay. I think that's covered everything I wanted on the assignment sheet. You can skip the wavelength thing, okay? Unless you already knew this. If you, like, I've known the colors of the rainbow since I was 2.5 years old, then okay, find me a book and write the wavelengths out, because you need to take it to the next level. Yes?
So a green screen only absorbs green and then like everything else no? Or
Nope.
how does that work?
It's absorbing everything except green. Green is getting reflected.
Yeah.
Yes.
How do you figure out the wavelengths?
You'd have to look it up in a book
Or on the internet? Can you look it up on the internet?
if you want to, if you're just dying to know what the wavelengths are. Okay, I think that's it for this week. I hope that went a little better than last week. You don't look quite as, they're not quite as brain dead, are they? How are you, Conrad? Yes.
Thank you.
You're welcome.
Chloe's in our backyard.